Good morning, everybody. Today we'd like to give you some insights into our current automation pipeline, insights of our company Vandelbots, how we move from CAD data all the way to OpenUSD, and the key role Blender plays in making that possible. So I'm Lars, I'm software engineer at Vandelbots. I'm responsible for the simulation and virtualization area. Next to me is Julius. He is working as industrial designer. He's focusing on onboarding robots and tools and building sceneries in Blender. And there's a third person. He's not with us today. He's also working as industrial designer, and he's an expert when it comes to visuals, geonodes, and scene optimization. We will do our best to represent you, Vitus. Hello, Vitus. And let's get started. So maybe you remember when you entered yesterday the building, maybe the first time. I directly had in my mind this image I took some years ago. This was on the gallery in our one of the first offices. We are not there anymore. And maybe you can see downstairs some little robot. That's what we actually do. We provide a robot-agnostic platform that allows you to control all robots across different manufacturers and create custom applications. But you might ask, okay, why is Blender part of the story here when you see only this physical robot downstairs? That's exactly what we will present you. We are not only controlling physical robots, but we also it's also important for us to simulate in a virtual environment beforehand, before it goes to the physical shop floor. And that's what you see on the right side. It's the virtual counterpart of the physical FANUC. So here you can see what Blender plays in our pipeline. We always start with the material creation. Blender lets us alter, preview, and manage materials that later flow into both virtualization and simulation. And we also use Blender, logically, for animation. The Blender animation system allows us to prototype robot motions and scene interactions. This helps us visualize workflows before they are simulated or tested on real robots. Then, yeah, marketing, what we do now here. Blender is also key for creating visuals, animations for marketing and communication. Then there's also the prototyping aspect of Blender. And what Julius will go deeper into is the robot onboarding, the tool onboarding, and also the creation of sceneries. That means cells which will then end up in the physical shop floor later on will be built. The assets will be created in Blender and then exported to USD. And as mentioned, USD is our go-to format, because we are not only working with Blender, we are working with different applications. Especially for simulation, we started a couple of years ago with NVIDIA Omniverse, because for us it's important to have the physical accuracy. And here we visualize the entire, it's not totally automated, there are a couple of manual steps in there, but this is the pipeline. It always starts from idea or customer request, and then from there we decide whether we need new assets or we can just reuse what's already there. Our in-house library feeds scene assembly with robots, tools, and periphery components. The third-party assets are used to build entire shop floors and factories, because there are a lot of existing assets out there, so we can just reuse them. And if we have all assets together for this for the scenery, we can just put them together, connect it to our product, Vandelbots Nova, and then we can create, because then the robots are moving, we can then create visuals and prototypes. and we can then directly convert it to OpenUSD via the Blender interface and simulate it in NVIDIA Omniverse or directly in Blender, depending on the physical accuracy we need. So I will now hand over to Julius. He will give you some insights into robot onboarding.
Great. So after the idea stage, we ideally move on to the scene assembly, but for that we need assets. Many of these already exist as third-party models. You can source them from platforms like GrabCAD, Sketchfab. Through the quality can vary quite a bit, but for most of our work we don't really need complex, fully rigged characters. Static geometry is just fine. So the CAD data from clients and partners covers a lot of ground for us. Shop floors, workpieces, and tooling is covered by them mostly. Where it becomes more interesting is with non-static assets, especially robots. That's where our in-house model comes in. Alongside robots, we also create tooling, like at the end of the robot, and peripheral elements to complete the scenes. Maybe sometimes those need animation as well. Let's hop into our CAD import. When we start onboarding a new robot, the first challenge is CAD conversion. Many of you will maybe be familiar with this problem. The CAD world is quite fragmented with countless proprietary file formats, and converting between them is very, very difficult. And that's why we rely on STEP as the common denominator. We need accurate 3D models, not just for visuals, but to extract something called the Denavit-Hartenberg parameters for each robot. These parameters are the basic mathematical description of a manipulator's kinematics. Manufacturers provide most of the numbers we need in their data sheets, sometimes. So we measure directly from the models just to be sure. Once we have a robot in a usable format, the problems don't stop. STEP is convenient, but imports can and will most of the time fail, at least sometimes. Geometry breaks, hierarchies get lost, and there's no real universal fix, so manual cleanup is always required. I'm sorry. And this cleanup matters. These models are not just for visuals, but they must be accurate. We need the precision for colliders that we create with our robot models, so the robots don't collide with themselves, like link for link, or with safety zones, or even humans. That's why we always use manufacturer models directly, never pre-modified ones from some sort of marketplace, to preserve this accuracy. Here's an example of the manual CAD workflow that follows. The geometric accuracy is one reason why we do this import, but visualization is equally important. So missing faces and stuff like that can't really be tolerated. And filling in some gaps is just a little bit more complex than pressing F in Blender to fill it. Curvature continuity has to be restored carefully, and when done properly in CAD, the result is a smooth reflection with clean surfaces that will work technically and also visually. Now we have our CAD data, the cleanup is done, and we face the next step, importing into Blender. This is not as straightforward as you might think. Tessellation in CAD can be tedious, and important data like hierarchy often gets lost in the process. One of the reasons we use Blender is its very extensive add-on ecosystem. For this stage, we rely on the Instalot add-on. This allows us to bring our clean step files in quite efficiently. No need to know the ins and outs of the tessellation settings of each CAD file like Rhino or SolidWorks, just one click and it's in. Even after importing, the geometry most of the time is still absolutely massive. CAD models are designed for precision manufacturing, not for real-time performance, so the polygon count is mostly far beyond what we can work with, and optimization is just part of the process. So we reduce complexity for two main reasons. First, many of these models end up displayed in web applications, so for smooth performance there, we target a maximum of around 100,000 polygons, plus minus. Second, our scenes are not small. When you place a robot into a factory-scale environment, dozens of them may be visible at once. Without optimization, performance quickly collapses, and that's just not acceptable. So reducing polygon count isn't just good practice, it's essential for scalability. Accuracy is still a hard requirement, so simple tricks like Blender's remesh modifier don't really work for us. we can't afford to lose the precision. So instead, we use again insta-lot for optimization. It lets us reduce vertex count often by half, while keeping the geometry quite accurate, at least accurate enough for our needs. That gives us models that are lightweight enough for the web and also suitable for USD export. Materials are another area where reuse really pays off. With always reoccurring brands, we also see reoccurring materials, and instead of rebuilding them for every project, we maintain a shared library. This makes sense at scale. Many assets mean many materials. Blender's principled BSDF shader also exports quite cleanly to MDL within USD, so the same shading library can be reused downstream. This ensures consistency between Blender and our USD workflow. And maybe keep your eye out for our shader ball. It might make an appearance back later. Once the geometry and materials are ready, we move on to rigging, but we do it our own way. No nodes, no armatures. Robots are controlled through the Navitatenberg parameters, so the structure is always the same. Parent-child relationships, empties stacked upon empties, and empties defining each joint. Doing this manually is quite tedious and very time-intensive. That's why we use an in-house add-on developed by my colleague Bruno. It takes the standardized DH parameters and automatically builds a clean hierarchy. The result is a rigged robot that can be exported into multiple formats. For us, it's GLB for web applications and USD for reuse in Omniverse. This is what the finished robotic asset looks like after the full pipeline has been run through. Clean enough geometry, more or less, optimized polygon count, materials, and correct empty setup. Now imagine doing this process not just once, but hundreds of times and across multiple manufacturers, each with its own quirks and edge cases. That's where you get this, our full collection of robotic assets we've built, including all 5 major manufacturers: Universal Robots, Yaskawa, KUKA, ABB, and last but not least, Fanuc. By standardizing our process, we can handle all of them consistently, and the result is a library of robots ready to be used across all our applications. Now we get to actually use our asset. Here you see one of our robots running inside our web application RobotPad. This allows us to jog, review, and program robots directly in our browser. Again, as I mentioned multiple times, performance is critical here, and so are the colliders. The model prevents self-collision and respects defined safety zones, so every move stays within realistic and safe boundaries. You can even set your safety zones manually and have the robot respect them automatically. Now it's time to bring everything together. In Blender, we assemble full scenes, robots, workpieces, tooling, scenery, and the smaller flourishes that make it complete. The exact requirements may vary from project to project. Sometimes we build large production environments, other times it's more compact. And not every project even involves robots. Some are purely marketing visuals. Scene assembly is where all the assets meet and become a coherent deliverable. There's a lot more, but nonetheless, there's a lot more to do until we actually get to robot programming and path planning. The scene planning, of course, begins much earlier than just plopping down some robots and starting. The first step generally is rough reachability testing by manually jogging. Jogging in this case means moving the tool at the end of the robot manually in directions X, Y, Z, as you might know. This is also something that we can do in Blender. As soon as you know what parts of your workpiece your robot can reach and what parts it can't, you can make a decision on robot placement. Maybe you even should consider a different robot with either a smaller or bigger reach. Next comes the planning of TCP positions. TCP in this case stands for Tool Center Point, the point where the robot gets its actual work done, so in this case, the welding point. This is something that can be done in Blender as well. We position empties, as you can see, on the point the robot should move to. Then we can read out the empty positions from the blend file and read out certain geometries with which our arms should not collide and use this information to start path planning. Then you get this. If we want to make the placing of the empties easier, we can use ghost teaching, a bit more refined technique. We parent the TCP empties to the end-of-arm tools and workpieces to get a good feel for the positions they will actually end up in when moving. These instances are also a great first step for just rough collision avoidance, just looking at the scene and determining what it might collide and what it might nudge in the process. On top of these practical implications, implications, it also gives us a first chance at roughly animating the interaction. Using constraints in Blender will come in handy at a later stage especially. Now, put all of your TCPs after each other and you get robotic paths and joint motions. On the left, you see a standard approach. We connect tool center point positions using Python, and the robot moves along these paths. You can try different configurations and choose how the robot should move. On the right is smart path planning. Here the system automatically avoids collisions and finds feasible trajectories, reducing manual effort and making the motion safer and most of the time more efficient. Here you can see it won't collide with the strut supporting our workpiece. Now, I hand over to Lars to talk a bit about Nova.
Thank you. So yeah, let's talk Nova. You heard the name already. Nova is our operating system to control both physical and virtual robots. The key idea is that it's robot agnostic. You can see here different manufacturers. For us, we don't actually care about what robot manufacturer or model we actually want to control, if it's supported. Through that single interface we provide, you can program control robots from, as mentioned, Fanuc, Universal Robot, Yaskawa, ABB, and KUKA. And we have on the physical side already 300 models integrated. And you saw the USD file which Julius showed. It's not 300 yet in the virtual space, so we have quite some work to do yet, but it's most likely on customer request because it takes some time to create those robots in the virtual space. And for us, it's important that it's robot agnostic because typically on the physical factory, it's almost never the case that you only have one robot model in the shop floor, but different manufacturers. And that's why we provide this solution to remove this complexity. And next to our operating system, we provide you platform, which allows you to access it via OpenAPI or Python or whatever language you want to use. And for the simulation environment, we are using ISAC Sim. A couple of years ago, we started integrating with NVIDIA Omniverse or ISAC Sim because the physical accuracy is extremely important. The simulation in the virtual space must reflect the real world behavior as closely as possible. The collision handling, the kinematics, and the timing, they need to be reliable for us. Otherwise, it could happen that what you simulated is not possible on the physical shop floor and then it crashes, and that's expensive. In the virtual world, we can just crash in a table and nothing happens. And on the right side, you can see the user interface of ISAC Sim, and there's a window overlaying. It's our extension. It allows you to directly select the robot you have put into the scene and click on connect, and then it's connected to Nova if you have a user account. But why does it actually matter? It's also you can see multiple robots here. We can also simulate multiple robots in parallel, so you don't need to program each robot individually on a new system of Nova. You can also program them with one Python script, and it does not matter whether it's the same manufacturer. You can also have a KUKA, Yaskawa in one script, and they work with each other. So, and this extension is publicly available. You can download it. The only thing is you need Nova, and then you can directly connect it. And besides that, in order to allow the robot movement, we also have an internal Blender extension, which allows us to connect to robots directly inside of Blender, very similar to our ISAC Sim extension. And from here, you can directly load our Nova configuration, select a robot, and establish then the connection with just a few clicks. And that makes it also possible, for example, for Julius and his team to evaluate the new robot assets prepare scenes without actually leaving Blender. And most of the time when we create visuals for presentations, demonstrations, or marketing, this is also really helpful, especially if we don't need accurate physics simulation. So, and with some clicks, you then have those moving robots. They are programmed once, and then independent to the tool, they move as you programmed them. And since we want to talk about OpenUSD in more detail, we also created our custom OpenUSD extension, which allows us to select a tool, because a robot without a tool or an end effector is not really useful. And Julius already mentioned that we have a ghost teaching methodology. That means you right-click on the tool, it's then, it gets then the data that it's a tool, and then we can create those ghost objects with the correct TCP, the tool center point, and can place them in the scene and can move along those objects and create programs without touching Python in the first place. Additionally, we also created collision-free planning. That means with OpenUSD, it's possible for us to directly fetch the colliders if you define them in the scene. And then we directly can fetch them inside of our Python program. We will also provide a one-click solution in a couple of weeks, where you just click, okay, export the collision world, and then the program respects that, and you can directly move. And that's pretty exciting. So you can see here one sphere was selected and the convex hull was visualized. And this helps then also for planning collision-free movement. So you can see in the terminal that it's calculating. It's not necessary to calculate it all the time. You can also then save the trajectory which was planned, and you can re-execute it all the time. So that was Nova, and now back to Julius to talk about some visualizations.
Now that the robots are connected, moving, and performing tasks, the next layer is visualization. We add scenery, periphery, animate the work pieces themselves, which is a big step. These elements turn like boring technical assets into quite nice marketing visuals, if I might say so, that communicate our process quite clearly. And in the end, you get a result like this. A fully functional welding cell with 4 robots working synchronously without colliding and with movements that can easily be replicated in the real world. That being said, this is just a scene for demonstration purposes. No real hardware has run this. Even the workpiece is custom made by us for demonstration purposes, just to really get to the point what our capabilities are. But this is also a good example of how we use Blender in applications that join real world and virtual components. If you remember, I was speaking about using constraints earlier, especially the child of constraint is used very heavily here. It's a great way of animating the gripping of the workpiece and then parenting it to the moving sleds, for example. Now, onto some more examples of Blender usage at our company, which might include some less robotic examples. The first thing is, if you need to move really fast and the deadlines are approaching quickly, we can always count on Eevee to help us get the looks just right for some customer projects. But sometimes we have some more time, and we even can use cycles to do things like mock-up design. On top of the dynamic scenes I already showed you, we use Blender for design mock-ups, like this click dummy of our own software called Robopad that you have already seen. Quick preview renderings, posing the robots with Nova and then exporting into Blender for scene assembly and materials is what Blender is just best at, and we use it all the time. Now getting a bit more into the real world. In this example, we see a virtual prototype of a real demonstrator for a research project. Here we use Blender for developing the looks and getting a feel for the end result. Afterwards, this demonstrator was built with slight variations. There will always be some missing links. One other use case for Blender at Vandelbots, a bit further away from robotics again, is just plain old design for 3D printing. There are the basics like grippers for robots and general mechanical devices, couplers, but also this little cute astronaut. The astronaut was a small project for giveaway during our launch event. But it also shows quite nicely the broad usage we can find for Blender at our company. Getting the looks dialed in beforehand is of importance once again, and I think we managed to make it look quite nice. And one last visualization project before we get back to robotics. This is our unofficial mascot named Arc. This time using Blender to do what it does best again: smaller scenes, awesome renders, and quick iterations, using the non-linear editor and stacking animations to get lots of variations and a lively feeling. These still renderings show the final stage of our visualization work, including robotics. We composed many smaller scenes into a complete digital factory, again using USD, attempting to reach a broader audience. The audience is mainly visitors at trade fairs coming from automation background and engineering. As you might imagine, simple animations are not enough, but these visualizations communicate quite nicely to even a more technical audience. Now, back to Lars for the final steps of our pipeline and a deep dive into USD.
So what's actually OpenUSD? I guess most of you know Pixar. Back in 2016, Pixar open sourced their universal scene description, USD. And if you are not familiar with OpenUSD, think of USD as a common language that allows Blender, iSyxim, Vandelbots, Nova, and other tools to talk to each other without losing detail of meanings. For me as a software developer especially, one of the most powerful aspects is that USD files can also be generated programmatically with C++ or Python. I chose Python. And that means we can automate scene creation, integrate data pipelines, and make robots part of the same ecosystem without manual steps slowing us down in the future. So here are some key aspects of OpenUSD. So the first thing is scene assembly. Here you can see a digital factory. You can think of USD as Lego bricks for digital factories. So instead of you have one big block, which was pre-made, we have many small pieces, robots, tools, work pieces, and even the floor. And then we can switch variants, load only what's needed, and layer the design, the simulation, the robot logic without overwhelming each other. And it's not just about geometric, it's also about data. Every object can carry attributes like material, speed, or process values from Nova. And that way, design, simulate, and execution all use the same source of truth, the OpenUSD file. And then rendering the instances of huge factories are possible in OpenUSD if you have the correct renderer. And as a reference renderer, Hydra Storm was created. And more on that later. And the real value is also that Nova gives you the process context, Blender adds the design and visualization, and iSyxim delivers physics simulation. And I brought a small video a colleague, Paul, created, which brings all together in one USD file. Most of the assets were created in USD, for example, an environment and the layering, the arc, and so on. And here I will just play it. And it's also showing our current destination, where our office is. So because we moved into the office, our designers also used the CAD data which were provided by the architects to in Blender and in iSyxim layer everything together. We had the robots, we had the cells already, and we just put them all together in one scene so that we can then play around and figure out if the humans have enough space. That was quite nice to see. So, why actually iSyxim, not iSyxim, but OpenUSD, sorry. The power of Blender is that you create small assets, but you have limitations. So you saw here the digital factory in the first prototype had not that much fidelity. because it had only 9 million polygons. We had to work together. Multiple people worked on different areas of the assets, but we needed to bring them together and work together, so without versioning the files and saving them on a different place. And that's why we put all together in USD as an instance and layers. And that allowed us to have this digital factory rendered with OpenUSD with 120 million polygons, which is quite impressive. We know that Blender makes a lot in this area, so I'm really happy to see how it's evolving so that we can also build such scenes then in Blender entirely. So I'm not going that deep into OpenUSD because it's a quite technical topic. I brought you here those two YouTube videos. You can just watch them, especially the USD-driven pipelines. It's a BlenderCon from a couple of years ago, which goes really deep into the OpenUSD. And the first video explains why Hydra Storm has changed with Blender 4.0. And because, yeah, some spoilers. So Hydra is important as a reference renderer for OpenUSD, because if you build a USD scene in any tool which is supporting, because there's a long list of tools which support OpenUSD, you need a reference renderer, and that's Hydra Storm. What you see is what you get, so to say. So, and then consistent naming might sound like a small detail for us, but it's a complex pipeline. For a complex pipeline, it's quite crucial. And if every tool, every library, and every simulation steps refer to assets in a predictable way, we save a lot of time. And that's why we automated this naming convention system. Then to make sure our assets are named consistently, we came together, looked at our assets and the naming, and we figured out that on Windows, for example, if you have long names and they are layered in OpenUSD, for example, and then Windows pops up with a message, okay, the path is too long, you cannot open your OpenUSD file. So we are not reinventing the wheel. The Blender community has created countless add-ons that tackle similar challenges. And one of the strengths of this ecosystem is that almost every problem you encounter was already been solved, and we also use the extension which were provided by the community. And then something about GeoNodes. We are using GeoNodes to build scenes in a non-destructive way. You know what non-destructive means. We can iterate and make changes without permanently altering the underlying assets. And GeoNodes also give us a flexible procedural workflow. Instead of manually editing meshes, we define rules and processes that can be reused and adapted. This is especially valuable when working with robotic simulation, where assets need to be updated quite often. And with import nodes, we can swap meshes in and out simply by replacing assets. The node setup stays intact. So if, for example, our CAD team sends us a new version of a part, we just drop it in and everything stays updated automatically. And we also handle the UV unwrapping procedurally. And this speeds up iteration dramatically. It ensures that scenes remain consistent as they evolve. So now to the last part, it's simulation. And here you can see from Blender to OpenUSD, you saw what Julius demonstrated was always in Blender, and then we converted it to OpenUSD. And this is real-time rendering, and here are just 4 different perspectives of the same scene, and that's really quite impressive what the quality gives you. And the next thing for us is especially to bring the simulation to the shop floor. The first video shows you the one example of a web application which runs on Nova to control a palletizer on the shop floor. So you can imagine you are working on a shop floor, you need to palletize something, and that's in the interface you see. And you can see here the GLB file of the Fanog robot. Then the next is with our Blender extension. It's the same palletizer. The scenery was built with CAD, we imported it, we connected to Nova, and then the same robot moves, and then you can also put around the environment, the cell, and see if the robot reaches everything before you buy a expensive workstation with a graphics card. You can also run it on Mac OS. And then if you have it then exported to USD and in Isaac Sim, that's how it looks like. We can then apply the physics, for example, the suction gripper and the conveyor belt. And then we can also integrate the entire process. For example, controller IOs were sent via the robot, and then we are using the OmniGraph nodes to control the conveyor belt, the sensors, and so on. And this allows us to put multiple cells together, working together with each other. And so it's also important that you understand we are not only doing virtual. Here's the exact same cell in our lab. It's the physical robot, it's the same application, it's the same Nova, it's just executing as you expected, and it's accurate as in the simulation. So, and that's it with our presentation. You can visit us in Dresden. It's only 48 hours bike ride. It's some mountains are in the way, but it's quite impressive, Germany. And scan the code and visit our developer community so that you can also have some hands-on. So I guess we have some time for questions and feedback if you want to share any. Thank you. Yeah.
So the idea of robot simulation is not really new, that you know, so that it's around for 25 years or so. So there is software like Robotics, like Lumia, like systems, Ukasim. They can do offline robot programming, they can do virtual commissioning, meaning that you have a real robot controller, right, with a virtual robot. So what's your USP? Where's your market position? So what can you do? What can you do?
So for us, it's not about replacing any existing tool. So we are providing a platform. So we are open. Everybody can build what they want. And we are also working with different developers of simulation tools together to integrate our virtual controller. So our USP is mainly the virtual controller, so that you don't need to buy a robot a controller license of the manufacturer if you just want to play around, because we entirely virtualize the controller of the manufacturers. And we are not doing offline programming. That means we are not exporting the code for the robot. We are the Nova system needs to be connected to the robot, but this allows us also to feed back the data from the robot, because if you need the data of the robot, you need a system there which translates the data in a standardized format, and that's what we provide with our system. So if some manufacturer like Siemens also wants to integrate our controller, we are happy to do that, also with KUKA and so on. It's not about replacing them.
Yeah, but there is a standard called RRS2.
Mm-hmm.
It's the World Simulation Standards 2, which is a standard. So how do you relate to that? Why did you create something on your own?
We started creating that before the standards was evolving. We are in the committee. One colleague of us is in the committee, so we are also happy to use standards which are existing, but it was not ready for us. But this is not my sweet spot, so if you have...
Because RRS2 is at least 20 years old.
Yes, but the standard so that the robot manufacturers adopt it is taking quite long, and that's why we are not, at the moment, not rely on that. But I'm not from the robotics. If you want to reach out, then happy to connect. Any other question?
I'm wondering, what is stopping OpenUSD from being earlier in the pipeline? Like, would it be possible for the robotic, the hardware creators to also use OpenUSD and sort of like directly give that to you? What is stopping that pipeline to be easier?
At the moment, we are using, for example, Rhino, which has directly an OpenUSD connector, and the support of OpenUSD is way better. With that, we can bypass some steps in the pipeline, but since for the robot onboarding, for us it's easier because the knowledge in Blender is spread more widely than with Rhino, for example, and that's why we added this process. But maybe you can talk about this. Yeah. Yeah.
So what we didn't show you today is the tool onboarding process, which is something I'm working on currently. There we are aiming to cut down the steps significantly, so the manufacturers themselves can do it for us, so we don't really need to do it all the way. But Blender is still like a very optional step between the CAD system and the OpenUSD, because it's much easier to tell some CAD engineer, hey, you can apply your materials in Blender instead of using ISAC because the mesh manipulation and extra required steps of reorganizing the hierarchy and stuff like that is just much more accessible in Blender in the free and open software. Okay then. Thank you all for listening, and have a great BlenderCon.